Okay, I think most students are here. Let's begin. Okay, so maybe after we finish this lecture that we left over some additional stuff last time. Okay, what we will do is we will ask all of you whether you want to do an assignment extension, because I got email from student asking for 1 week extension. Okay, but unfortunately we will not be able to wait till 1 week later to assign you the next mini project. Okay, and so there are still one more mini project and one more written assignment to go. There are actually 2 mini projects, but probably we'll cancel one. Okay, so that we only have 3 mini projects altogether, right? So, and so that you will have enough time to work on the final project. Maybe that's a better idea. So for the upcoming, there are 2 written assignments still to go, right? So, and 1 mini project on Newton's method. Okay, finally we'll have a final project. The final project will be basically on object detection. Okay, but you can select other topics to discuss with me. Okay, the reason we specify this particular topic is because the department has a conversation that some students reuse their projects to different data science courses, right? So like data mining, machine learning, deep learning, right? You can reuse it, right? In NLP, for example, NLP is also machine learning, right? So to avoid that, we are asked to give specific projects, right? So one particular idea what I'm trying to do is because all of you guys have annotated objects in the first assignment, right? So we have already prepared a collection of the image annotations for those drawn images, okay, on transmission tower parts. And we will share with you guys so that you can work on the project using this data, right? So in this way, you cannot reuse in some way, okay? At least for our course, you cannot reuse another data science course project for other course. Our course, okay? Because the data set is specified here. And hopefully this will work out well, okay? But if you want to work on other topics, you need to discuss with me, and then probably we will communicate with other data science professors to make sure that the project not reused for other data science courses, okay? And then if the difficulty is comparable to the final project we specify, okay? So then it's okay, right? So if, for example, you are a PhD student working on some medical imaging data, right? So for example, or work on some other like natural language projects that can use our mod, what you learn, right? So, but if it's a trivial, let's say pandas loading and then some data cleansing, and then scikit-learn machine learning model call, that difficulty may not be enough, okay? Or you then use pyplot to plot some images. That difficulty is too simple, okay, compared with our specified project. In that case, we will not take that, okay, we will not consider that. Right, so, okay, let's begin. Hopefully we will have time today also to go through the final project, okay? And we will release it maybe tonight, okay? And the clock for the next mini project ticks right after the original deadline of assignment 1, which is Wednesday, right? So so we will release our next mini project on Newton's method on Wednesday, okay? And after that we will what we'll do is so basically for assignment 4 in this assignment, the Hessian matrix, it will be necessary to be used for the next assignment. So hopefully you can finish it by Wednesday. But if you cannot, we will not have any late penalty until maybe 1 week later. But before doing that, I would like to ask you guys to solicit your, idea on whether you want to extend it and when you want to extend, maybe for this Friday or next Monday. What we will do is, because in Zoom we will have the hands, right? So I will just look at the Zoom participants. If you want an extension to maybe to this Friday, let's first ask this: if you want an extension to next Monday without a late penalty, okay? But we will release the next mini project anyway this Wednesday, okay? Which will be required to finish this assignment and use a conclusion, by the way, okay? The mini project will last for another 2 weeks, okay? So if you are considering to extend to next Monday, you think it's necessary because midterm, this is what I heard from a lot of students. There are a lot of midterm exams, right? So can you raise your hand in the participant?
Yeah.
Okay.
Raise hand.
Yeah. So the reason I want to do this is because just in case a lot of students already finished, right? Then it's unfair in some sense because some students finish. So in case you don't know how to raise hand, so there's a button there, down there at Zoom. Okay, so where you can do this. Okay, I see a lot of students raising hands, but the majority are not raising hands, right? So okay, let's see.
Yeah,
Okay, so
I raised the hand, but
let me see how can I lower hands. Yeah, I see quite a lot of students already raise hand. Okay, let me clear the hands. Okay, I think it's pretty much there. Okay. Clear all. So how many students want to extend just to this Friday?
Professor, you can do a poll as well on Zoom. I think that would give you
I cannot hear you. Can you speak louder?
I said you could probably do a poll on Zoom directly. I think that will give you better data, sir. If you
Oh, so how can we do that?
I'd like to have it.
you should have a poll option under in Zoom beside participant. I think you should.
Oh, really? Let me see. Oh. Yeah, I probably didn't enable it, so I cannot find it. I only have invite, mute all, and more. More, I cannot find the poll. Okay.
I didn't see where to raise the hand. Sorry.
Where to raise hand? Oh, okay, let me see. So yeah, I cannot see
Here, I got it.
so basically there's a button down there where you can click and then you can raise hand somewhere. But yeah, because now my panel is not your panel, right? So I'm sharing screen, I cannot see it. So
it's in the participants tab.
Okay,
okay.
I got it.
Yeah, how many students don't want to extend? Let me clear first. Okay. Yeah, because I cleared. So here's what I would do. So I do see some students don't want to extend. Maybe it's a bit sensitive, so not many people are raising hands. And I also see a lot of students for this Friday, and then another lot of students for next Monday. So we will extend to this Friday. I think that's probably a fairer solution. Okay, so because we need to consider fairness, right? So some students spend a lot of time to catch the deadline, and then let's first extend to this Friday without any late penalty, okay? And let's see. What we will do is assignment 1. We'll extend to this Friday, okay? I think that's pretty much it. Okay, so yeah, some students seems to already submitted it, right? So because there's something say I cannot change, etc. Okay, deadline is still okay to change. Okay, so I understand a lot of students may have some worry about one particular assignment, which is a key assignment, right? That's question, one particular question assignment, question 4, okay? So if you are attending this lecture, we will provide some hints to you. Basically, we will give you almost the solution, okay? But we will only do that, in the class. So you have to watch video if you don't take any note later. Okay, so we will share the video on YouTube. Okay, for our student, please ask Gopi. Okay, so yeah, and right. So let's begin. So last time what we see is linear discrimination and the logistic regression, right? So and we said logistic regression is actually to to predict the probability that you belong to the positive class. Okay, So the probability is kind of like a regression, but the regression between 0 and 1. So this is not exactly regression. Okay, it's more like a density estimation, right? But actually, once you have the probability, you can define a threshold. Then you can have, let's say if it's 50%, which makes sense, right? If more than 50% you are positive, then you are positive, right? So this actually translates the problem into a classification problem, okay? But you can make it more strict, right? So stricter. For example, only when I'm confident that 90% I'm positive, then I will assign the class to 1. This may happen, for example, in the cases that let's say you want to find competent students, right, for some research projects. And then maybe in a class of 100 students, you find maybe there are already 40 students, right? I want to be more strict, right? So maybe I will level up. Oh, sorry. So I cannot find my mouse again. Just one. Okay. Maybe I want to level up this threshold. Okay. When I level up this threshold, maybe I only have 5 students, but that's all I need, right? So for example, okay. So that's basically you can change this threshold to make it stricter, right? So when you change this threshold, right? So the probability will change, and then your class, which are positive, which negative actually will change, and this will change your positive rate, right? False positive, false negative, true positive, true negative, and these rates will change when you change this threshold, okay? This threshold tall maybe, okay? And this will give you a curve for different maybe recall precision, etc. So there's a precision recall curve. You can also have a ROC curve, okay? And the area below ROC curve, AUC. All these are, due to you change this threshold, okay? Not just assume it's 50%, right? So, and if your ROC curve, this one is better if this ROC curve is on the upper left corner of the other one, then this one is better whenever you change different parameters, right? So this is what we one important concept. Okay, so several other things that you need to remember is that we have the logits, right? So what is a logit? Logit basically logit function, right? Logit basically log of your success probability divided by the failure probability, or the probability belong to C2, right? C1 divided by C2, then take log. Okay, it's a ratio, right? And what we do is we assume this ratio, you see this ratio, okay, is a linear function. Okay, this is what we see last time, right? We assume log of class 1 divided by class 2 probability. This is posterior, by the way. Okay, you see X and this, okay, is a linear function. Okay, this is logistic regression, basically. Okay, our assumption for logistic regression. And I think we see sigmoid function.
Doctor, yeah, I have a question.
Okay.
Could you get back up that page?
Okay.
Yeah, the second line, how we get the second line?
You mean this line?
Yes.
Oh, because this term times this term equal to this term is okay. This is the prior, this is the the class conditional probability, right? This times this equal to this. Of course, divide by this is
Did you use the Bayes theorem?
What?
Did you use the Bayes theorem?
Yeah. Okay, if you want, I can do a derivation. I think that's actually covered somewhere, right? So this is last time stuff, but let me do the derivation for you, okay? In case some other students also don't understand. Let me see.
Last time it was not done, I saw. Okay.
Yeah, so this is equal to what? This is equal to P x C1 times P C1, okay? Divided by Px, okay? Right, so this is equal to something similar, but it's C2, okay? Divided by Px cancels, right? So basically log of this thing and the log of this thing, these are two terms, but C2, okay? And now, if you think about this term divided by C1 and XC2, this term as one term, like say A, the other term as B, okay? Right? So this is basically saying that this is log A times B, right? Equal to log A plus log B. Any questions? Yeah, so
We're
it is
just extra areas.
what?
So we're just doing the a posteriori, right?
Yeah,
Posterior probability. That's what we're just doing.
this is posterior probability, right? So this is prior. Yeah. So do you understand what I did, Sami?
Yes, yes, sir. I
I
understand.
hope you
So
understand. Right. So yeah. So let me see. So maybe we can. So let me use a pen again.
just finding posterior by multiplying the generative probability.
Yes, this thing is equal to this thing times this thing divided by px, okay? This thing equal to this thing times this divided by px, right? Okay, so this whole thing is equal to this thing times this thing. It's okay?
Yes.
Right, so if this is A, this is B, right? This is log AB, okay? Log AB. This is, if you take this is log A plus log B, right?
Yes, yes.
Yeah, I think this should be fine. Okay, any other question about this formula?
Okay.
Yeah, anyway, so this is not important. Okay, so this is details. So just keep in mind what we need to pay attention is this, okay? So logits, right? Log you belong to class 1 divided by class 2 is a linear function, okay? So this is all you need to remember. This is our assumption, right? Based on this assumption, we can get this conclusion, okay? This conclusion basically says that, you know, the probability that you, posterior probability that you belong to the positive class is equal to 0, right? So this is a sigmoid function, but this term, you know, A is equal to this, okay? This is a linear term, okay? So this directly computes the posterior, right? So basically if you have a row attributes, right, it's a weights W1 times X1, W2 times X2, etc. Okay, and plus bias 0, right? And you put into this term, you immediately get the probability that you belong to the positive class. If it's larger than 50%, I think it's positive. Otherwise, it's negative. Okay. Yeah, so this is sigmoid function. This is more like a threshold, right? Initially, it's 0. And when you go beyond the critical point, like 0, right, it goes to 1. But, you know, in machine learning, we want something differentiable, right? So we have this curve, okay? We cannot just have a threshold function, right? So if we have a threshold function, it will look something like this, right? So you have something here, and then when you pass 0, it goes to 1. So sorry about the pen. Okay, it should be straight, okay? Yeah, so it's not easy to locate. Anyway, so maybe I can directly use mouse. So basically you have here, and then suddenly after passing 0, it goes to 1, okay? So, but we want to take gradient, right? So we cannot do it, okay? And yeah, so the reason we cannot do that, we need a smooth function to take gradient because you think about it, right? So if your function is something like that, right? So it's a gradient infinity, okay? If you have a curve, something like this, suddenly go, the steep is infinity, right? The gradient is infinity, you cannot handle it, right? So on the other hand, if you have something like a ReLU, this can be handled, okay? So something like if you go beyond 1, it becomes x equal to y, okay? Otherwise it's 0. This is called a ReLU function, okay? If you have a function like this, right? So basically ReLU function will be something, another activation function, okay? Something all the way 0 until this, and then you have x equal to y. This function, you can take gradient, right? So the gradient here, the steep is 1, right? It's unlike here, you have infinity, okay? And here, the gradient is 0 because it's flat, right? This place is a little bit special, okay? This place, we can say it's 0 or it's 1, right? Because it's not smooth. On this side, the gradient is 0. On this side, the gradient 1, right? So in general, you can see the gradient is between 0 and 1, right? So anyone is fine. So basically, you can take any line steep is here, right? For example, if you take this line, right? You did not cut into here, okay? If you take this line, it also does not cut into here. Until you are here, it's still not cutting to here. But if you take this line, it's cutting to the internal here, okay? That's not, right? So this whole thing is called a subgradient, okay? If your function not smooth, there's some like this kind of tip point, right? So then you have a whole bunch of gradients that are valid, right? You don't cut into here, okay? Because, you know, as long as you don't cut this gradient, right? But in this kind of non-smooth point, you have a lot of them. All of them become a set of gradient values, right? So this is called a subgradient, okay? And there's still a theorem saying that if your subgradient contains 0, right, then your function is convex. Let's say this is convex, right? Given any 2 points, it's above it, okay? But it's not smooth, okay? There's a tip point, right? If your subgradient contains 0, which is the flat direction, okay, right? And then this is also the global minimum, okay? So it's a generalization beyond the smooth function, okay? But the, we cannot take structural function because the gradient will become infinity. And yeah, I will be back shortly. Okay, let's continue. And let me see, so where we were last time. Okay, so I think we were quite ahead. I think it's page 30, 32 or something. Just, so last time what we see, just a recap of what we see, okay? So we were here, right? So last time, I hope you watched the YouTube video. I see 22 students watched it, okay? So last time we showed that, if you take gradient using chain rule, this is 3 parts of chain rule, okay? The first part is, the first part is using the logics, okay? Using this function, okay? You take gradient, the y will become r divided by y, okay? So this is the first part. The first part is here, this part, okay? The second part is, then y, what is y? Y is a sigmoid function of a, okay? So when you take a derivative y, you have y 1 minus y, okay? And finally, a, what is a? A is a linear function, okay? A linear function. So basically, if this is, wj times xj, other term has no relevance to wj. So when you take derivative wj, you only have xj. So these are 3 parts, okay? And last time we showed that it's a nice property about this derivation is that this term in the middle, seemingly long, but you can simplify into this one, okay? So basically the real value and your predicted value. Keep in mind y is what? Y is your probability prediction, right? So the positive class probability, okay? Y is sigmoid of a, which is a linear function, okay? So yeah, so this is what we have here, right? And so doing gradient descent using this, and this is basically the same derivation. It's just that the last part, when you take gradient, you take gradient W0, right? Times 1, okay? So this term is gone because this is 1, okay? So you times 1. Right, so this is our derivation last time. And this will be reused again. Okay, keep this in mind. This will be reused again today, right? And let me see. Yeah. So
I'm not sure what
next.
the W represents.
What?
So I don't know what the W represents here.
Oh, okay. So W is the weight. Okay, so weight is this, is in this W. Okay, so basically this is the inner product between W and X, right? So W1 is the first parameter times your first attribute, X1, the first column of your data, okay? Plus W2 times X2, okay?
So then is A the class estimate?
A is just a notation of this thing, okay? We just simplified A into this. Right, so put simply, let's go back to here. Okay, so because we want to use chain rule to simplify the derivation, we're saying this term is A, is okay? Right, and this term is Y. Is okay? Do I answer your question?
So and like running through this derivation helps us create the sigmoid, which tells you
Yeah.
where the class property is, like how to estimate the class or the class estimation.
So yeah, exactly. So this is A, okay? Sigmoid A is just a 1 divided by 1 plus A, exponential negative A, okay? A is this linear score, okay? And the after sigmoid, this is exactly the class probability. Right? So if it's larger than 50%, you belong to class 1, okay? Otherwise, you belong to class 2. It's okay?
Okay, yeah, I think so. Thank you.
Yeah, so if you are not familiar with this, you have to get yourself familiar with this. Okay, so that takes time, which we cannot address in this class. Okay, there's a video and there's slide. Okay. But if you have question, I can clarify this. Okay, but then it will take time for you to get familiar. Okay. Yeah, so basically the first part is using this y, right? So, and then this y is the sigmoid of a, okay? And finally, a is the weight function, okay? I hope this is fine. So, and using this derivation, we'll get this, right? So one conclusion we have here. So I see a lot of students are leaving. Maybe it's a little bit they didn't review last lecture after this, and then this is too mathematical, right? So, but here I will directly go through the Hessian matrix, okay? So that basically give you hints on the assignment, right? So I hope these students will watch the video later, okay? Otherwise they have to derive that themselves, okay? So one thing you see here is that the model parameter W, right? So E partial derivative W is already here, okay? And we know that the Hessian matrix is what? Is E Wi Wj, okay? Right, this is E squared. Right, so this each element, the ij's element is this, okay? The Hessian matrix is just a matrix where the ij's element is something like this, right? So this basically already tells you, right? So this equal to this thing. Of course, there's a negation, you should be equal to. So E divided by Wj is equal to this, negative this, okay? So this is the conclusion of, if after we simplify, this is this, okay? So now all we need to, so by the way, this is J, right? So let's write it in, let's write it here in a more user-friendly way, okay? So basically this is giving you the solution for some assignment, okay? So E Wi, okay, equal to what? Let's change this J to I, okay, right? So this is equal to negative, okay? Summation of L, L is a data point, okay? RL minus YL, okay? Times XI, yeah, okay? And all we need to do is continue to take derivative of this term with respect to Wj, okay? Partial Wj, okay? So you can start from this page 30, and continue to that, and get the value of each element. Okay, so I don't think there's enough space for derivation. So let me stop sharing and use the whiteboard. Okay. Yeah, can you see my whiteboard?
Yep, can see it.
Okay, I hope that's working. Okay, so basically here, so the reason we want to prove it's a Hessian, right? Because even if you take gradient descent, right, you're not guaranteed to reach the optimal, right? So only when here is convex you reach optimal, right? If this is something like this, right? So if you reach here, this may not be the smallest value. Okay. I think I need to switch the mode. Yeah, this is much better. Okay, so previously what we mentioned is this conclusion. Okay, so from that slide, so that's number 30. Okay, so what we said is that E divided by Wi is equal to negative. Okay, L YL. Oh, so how to say this? This is positive. So previously in that slide, it's the RL minus Y. So we just write it as a YL minus R. Okay, then we don't need the negation sign. This makes things a lot easier. If you have your slide, you can also watch it again. You will see this. Okay, right. And then what we want to do is we want to further take derivative over this, and then further take this over the future. Okay, so basically we are getting this, right? Error Wi is equal to what? Right, so this is the question. Okay, so this is summation. We can take summation out. Okay, so if we take summation out, we are taking partial derivative of this part with respect to WJ. Okay. So what is this part? This part is YL XIL minus RL XI. Okay. But obviously, the question is, where is WR? Okay. What is WJ? Where is WJ in this function? Who can tell me?
In R.
The sigmoid of YL.
On YL, it's
In
W.
YL. Okay. So basically, we are saying this is the YX minus RX, right? And take derivative WJ. If this term has no W, it's gone. Okay. So we are just taking this term. Okay. And this term X is also relevant, right? You can write X, XIL. Okay. Only Y contains W, right? Because Y is sigmoid of A is a linear function of W. Okay. So all we have is this. Okay. So this is YL. Oh, WJ. Okay. So because this term is for W. Okay. Right. So this is where we have here. Okay. Now, how can we compute this term? This is by chain rule, right? Because Y is a function of A is a function of W. Okay. So this Y is a function of A. This will give you something like YL 1 minus YL. I hope you still remember this concluding. Okay. And then is A to WJ, right? A to WJ is XJ. Okay. XJ, because it's a linear function, right? So and then this, right? So simply what we have here is okay. L, and then we have this term YL 1 minus YL, okay, times we first write this term, okay, and then not this. It's the same. They are just scalar, okay. XI, yeah, XJ, okay. So this is what we reach here. And one observation is using autoproduct, right? So remember, this is the in the Hessian matrix. This is the ijth element, right? Okay. Right. So ijth element is xi xj. So this gives you an idea of autoproduct, if you remember. Right. So autoproduct basically, if you have x times xt, if they are vectors, where x is x1, x2, x3, x3. Right. So then this is the matrix where each element is xi xj. Okay. It's okay. This we have gone through that earlier, the autoproduct. Okay, just think about x1, x2, xd, and then x1, x2, xd, right? It's a column times a row. Okay, then it's the first row times the first column is it's I. Okay? So this basically says this hij, it's kind of relevant to autoproduct. Okay, but there's a summation, right? So we can think about this hij basically is a summation, like we have a matrix for each element, okay? And then it's a summation. So for each data row, yeah, okay, we have something like this, okay? YL, for that row, we have YL, okay? Right. And then times autoproduct matrix, okay? This is the times, how to say this? Times XL, right? So this is the feature times XL transpose. Okay. Basically, each term this is for one row. It can be a matrix. It's a summation of all those matrices. Give you a picture. Okay. I think we are running out of the space. Let me clear and write this only this conclusion, and then we continue derivation. Okay. So what we have is hij, right, is equal to, so what we have seen is it's a bunch of functions, hij, yeah, okay, but each hij is something like is yl 1 minus yl, right, and we have xl times xl transpose. Okay, we don't have arrow anymore, okay, because it's pretty clear it's a vector. Okay, y is a scalar, y is the probability of PCM. Okay, right. Okay, it's just a, this is the matrix, right? It's a output. It's a bunch of matrices summed together. One matrix is just summed together. One log. What we want to do is prove its Hessian matrix. This matrix is what? Is a positive sum vector, right? So basically, we are saying that given any vector v, okay, if we have its projective form with its edge, okay, and with so this thing will always be larger than right? How can we prove? Okay. So in order to prove this, actually we prove another condition to the even stricter. Right? So if we prove this, right? So if we prove for any matrix L, right, this value is going to be positive. Right? So because this thing is a summation thing, right? So basically you have if you have a V transpose, right? So you have V transpose and this. Right? This equal to a bunch of these. Okay. So if each term is non-negative, the summation is also non-negative. So what remains to prove is just this. Okay. Right? So how to prove this? Right? So I see a lot of people coming back. So then we just think about oh, there's no IJ here. Okay. This is not IJ. So this is basically saying that right. So if you have VT, have this constant. But keep in mind these are values, right? So these are constant. That's just a right constant. Okay. Then we have VT as H, right? H is XL, XL, O, and F. And next we look at this, right? This is a vector. Okay, this is a vector. This is also a vector. This is inner plane. Let's assume the V and X in the product value is A. Okay. You already used A. Let's go it maybe B. Okay. But this is again X and B. This again, right? And so this is basically CB squared. Right. So B square is like infinity. Right. So we want to show that C is over. Right? What is C? C is Y times 1 minus. Right. So this is what? This is PC1. It's a probability between 0 and 1. So these two terms are all non-negative. Okay? So the whole term is non-negative. And that's why for H, okay, so this is the other L. Okay? So the summation is 1. So this shows you that the Hessian matrix is a positive sum vector. Let's say for any B, right? So you get a B, you get a B squared. Okay? Right. So this basically completes the proof that this is convex. Right. This only holds if it's a logistic regression. If you go to neural network years later, then it breaks. Okay, only for logistic regression. Safely do this. Any questions?
It's really tough to understand you right now. I think somebody's unmuted. I'm hearing a lot of noise.
Yes, me too.
There's a
I
lot of
think
noise. Hello?
Yeah, Emmanuel, I think you're the one that's unmuted.
Yes, I was, but I was hearing the same noise that you were hearing.
Let me see. So let me mute all. Okay, so you whether this. I muted all. Is this clearer now? If you can mute it and let me know. Oh, it's still very clear.
Yeah, that's better.
I see. Maybe some students is opening their microphone. Okay, but does that impact the direction that you were reading?
It was really tough to understand what's going on. So the C, that's a scalar probability, right?
Yes.
And the B
C
squared.
is not a probability. This C is this part, right? So we write it like this. Okay. Y is the probability. 1 minus Y is C2. Okay. But their probabilities, they are non-negative. Okay.
Yeah, I thought you just replaced the Y's with that C, so that's why I thought it was a probability.
Yeah, it's a two probability time together if you want to say so for that particular.
Okay, sure.
Any other questions? If this is clear, is the whole process clear, or you have any questions?
One more on, I just want to understand all these variables. Like the B is
Oh, B is equal to inner product of V and X. Is okay? X there. Is that inner product?
Yeah.
Yeah.
I know X is like your class characteristics. I'm
No,
not sure what V
It's
is.
not a class character. This is the features, right? So this is the table.
Oh, okay, that's what I meant.
Yeah, this is features. Okay. Y V is any vector. We want to show that for any V, this is a positive 7 decimal, right? So this will always be larger. Is it clear?
Okay, clear enough.
Yeah. Okay. Then let's move on. If you have any questions, just let me know. I can clarify more. Okay. This video will be shared on YouTube, so you can take your time and yeah. Again, so taking time to understand. Okay, it will take time, but we cannot just this will take time, right? So let's move on. You get an impression, and then later you can rewatch. Okay, so yeah. All right, so now let's look at more than 2 classes, right? So let's say you have C1, C2, CK, okay? And so what we'll do is this, okay? So remember when we define logic, right? So we define logic something like this, right? So log P C1, P C2, right? Probability 1 and probability 2 is
I'm
equal
sure
to
if you're sharing your screen, but I can't see anything.
Oh,
Maybe-
I see. I shared the whiteboard. That's why. So just one moment. Thank you for letting me know. I need to. Let's see how to do this. Okay, so now let's consider more than 2 classes. Okay, when we have more than 2 classes, we cannot use P and 1 minus P equal to Q, right? So C2 is equal to C1's probability, 1 minus C1's probability. We cannot do that. Okay, so what we'll do is, remember we have log P1 divided by T2. Okay, I'm just writing P1 as PC1x. Okay, for simplicity, it's for class 1's probability. Okay, this is a linear function, right? WT times x plus W0. Okay, now what if we have k classes, right? So what we want to do is this, right? So we want to show that we want to assume that P1 divided by PK, the case class probability, is a linear function, one linear function, maybe W1, this one, okay? And then P2 divided by is another linear function, 2, 2, okay? Something like this. So this is what we are saying. So the last class will be treated as a reference class. Like in the 1 class case, P2 is a reference class at the bottom, okay? So this will, and here this will give us something like this, okay? Right, for each class from 1 to k minus 1, right? Except for the last class, the ratio of the linear function, okay? The last class, the ratio will be 1, right? So log is 0, right? Because we are taking it as a reference class, so we only care about k minus 1 of these logics, okay? And so this is just what we discussed last time, right? So at the beginning of the course, right? So this is posterior, this is class conditional probability times prior, okay? And we can write it down like this. And now, keep in mind that we show that this part, right? So let me still take the pen, okay? If you look at this part, this is equal to what? This part is this part, right? If you take a log here, this exponential, okay? So this is this part, right? Times this prior, okay? Prior, we can write it like this because log and exponential cancel, okay? And if you think about the exponential here, right? So this is just a constant, right? Of prior. So this is plus another constant, right? So you can write this constant as a 1 constant, okay? So we don't care about this constant anyway. So this basically tells you that this ratio is exponential of a linear function, okay? So this is what we have on this page. All right, so here we are saying that this constant is just this constant plus this constant, okay? This is equation 1. And now what we'll do is for this equation 1, we sum them up, okay, along both directions for all the other equations. So here is equation 1, okay? So here's equation 1, right, for a particular I. So what we will do is we sum them up, okay? Sum them up. but we only consider pk minus 1. So this is C1, this is basically here P1 plus P2 plus all the way to pk minus 1. Okay, and this is on the right hand side. This will be plus maybe 1, 1 plus E22 plus E33 to k minus 1 comes. Okay, so this gives us something like this, right? And yeah, anyway, you cannot understand, just let me know. And this is just saying that this is what? This is P1 plus P2 plus all the way to pk minus 1, right? Okay, and we know that the total, if you plus pk, it's all the classes, right? It should be equal to 1, okay? So if you look at this thing, this is really 1 minus pk, okay? Right. So this summation is 1 minus pk. And if we just look at this part, we'll get this part, okay? Let's just look at that, 1 minus pk, right? Equal to, let's write this summation term as s, okay? S times pk, right? So if you move this here, this is plus pk, right? So it's S1 plus s pk, okay? And then finally you divide it here. It's 1 divided by 1 plus s, okay? Right, so this is how we derive the pk. Okay. So previously we see how we derive pk, right? So it's pretty easy to see that this is a summation over the other exponential values, right? And now this is just for a particular class k, okay? What if we want to compute the probability for other classes, right? 1 to k minus 1, okay? The probability can be written like this, okay? So how to see this? If you go to the previous page, we have this conclusion, right? So we have this conclusion. This thing is equal to this, okay? Now we know that pk itself, you can write it like here, right? So times pk, right? So this pi is equal to pk times the exponential for this I, okay? Due to this reason, because pk is this thing, right? Divided by, so pk is divided by this, right? So pi is this thing times the exponential, right? Any questions? Okay, so here we are treating pk as a reference class, right? So we are treating pk as a reference class, right? So we can, if we want to treat all classes uniformly without having to choose a reference class, then we will get a softmax function. Okay, so what we are saying is that if you look at here, so we are saying this term is a set, you can generalize it to wk transpose times x plus wk literally. Okay, and we generalize this, right? So then the bottom becomes summation from I to k. Okay, and the top, this thing also is exponential, right? So it's of the same shape like here, but just this becomes summation with k, right? So then we are treating everyone equal. Okay, so you can see that it's basically everyone has a linear score, right? And you are taking exponential over the linear score and take the summation as the denominator. Okay, denominator, and the numerator is basically, the numerator is just the exponential of the linear score, right? So put simply, you first take a measure over the linear classified scores. Okay, after doing that, you normalize them, right? So because the reason we sum them up because they are probably sum up to 1. Okay, so we normalize them. So this is basically intuition from this derivation. So this gives us this. This is a softmax function. Okay, this is softmax function. The reason we say softmax is because if your score is large, right, compared to the other scores, after taking softmax, your score is much, much larger than the others, okay? Because it's exponential, right? Exponential grow quickly, okay? And if your score is larger, after taking exponential, you are much, much larger than the other smaller values to exponential, okay? So your weight is actually boosted. So this is called softmax. We can take max, right? So we can take the max of all the scores, but that will make it, again, not differentiable. Okay, we want to be able to take derivative. Okay. So the softmax function behaves like a max, but it has an advantage that we can take derivative. Okay. Any questions? if not, let's continue. Okay, so so now let's take a look at parameter learning in the K-class case. Okay, in the K-class case, we know that the yi now is a probability that you belong to class I, right? So because we have K classes, we have P1 all the way to Pk, right? And we know that this is multinomial trials, right? So basically, multinomial geometry probability is written like this. Okay, let me take something like this, right? So basically, this R is kind of the class indicator, right? So if you belong to class 3, then R3 is 1, the other is 0, right? So the other 0, this term becomes 1, okay? R3 is 1, then your probability Y3, right, stand out. So it's really, if you belong to class 3, your probability is Y3, okay? And then this is the joint probability among all the data rows, okay? Because we assume ID distribution of the table, data table, okay? And if you take negative log likelihood, right? So this is cross entropy loss, right? Cross entropy loss is equal to negative log likelihood, okay? And we also write it like the calligraphy, okay? And that usually means log likelihood, I'm taking log, because you have likelihood, you have log, right? So double L, okay? This L, this L. So it's a calligraphy L, okay? A very strong L, right? In terms of most notations, okay? And so, yeah, so basically after taking log, this thing comes down, okay? And log y, right? And the product becomes summation. Any questions?
Yeah, when would you want to use likelihood versus log likelihood?
We always use log likelihood because likelihood is a product, right? We cannot take a derivative, right? This actually we covered earlier. If you have p fx gx, right? So if you take a derivative, it's already very complicated. It's f prime gx, right? And plus f g prime. Okay. Now if we have hx, lx, etc., this is unacceptable, right? If you take a log, this becomes summation. Then when you take derivative, each term can individually take derivative. So we always take log likelihood because likelihood is always going to have a product over all the rows of the table.
Okay.
Yeah.
Why do we want to take derivative of the log likelihood?
We want to either compute e to each parameter set to 0 and solve the W analytically. This is the best W functions parameter.
Oh, it's for solving the weights?
Solve
Solving
the
for the best
weight.
weights?
Yeah, so these are the weights. Because these are the model parameters theta. Okay? This is f theta, right? Okay.
So by equating it to 0, what are you essentially trying to maximize the likelihood? Is that what it is?
Yeah, maximize likelihood. Yeah, or you minimize the error. Okay, this is cross entropy error. Right, taking negative, you are minimizing. It's okay. So basically, we are saying this, right? So your function is now linear function is something like a w1 x1 plus wd xd. Okay, plus w0. Right. Your table is something like x1 xd. Right. And you have a class y. Okay, class c. Right. So this is a table. Now these are the numerical values. Right. You want to find such w when you time these numerical values. So it's w0. Right. So these are the model parameters w. Okay. And finally, it will give you a probability where for your C2, for example, the class 2, your P2 is the largest. It's okay? Then you don't make mistakes, right? Otherwise, you have an error, and the error is measured by here. It's okay? This is the problem setting. I hope
that helps. Thank you.
You're welcome. Yeah, so then basically this is the error function. Okay. Right. So because we have the log y, right? So and y this time is a softmax operation of the linear scores. Okay. Right. So now we are treating this as AI. This is AJ. Okay. Summing over objects. Okay. These W linear scores are A. Okay. So now, because multi-class, we don't have sigmoid, we have softmax, right? So in that case, using chain rule, we first need to take derivative of y to a particular a, okay? Right? Because for each class, you have an a, right? AI is for ith class, right? So now for this step of the chain rule, we need to prove something like this, okay? Just like before, we have yi 1 minus y, right? Y 1 minus y. Here we have some more general case because we now have different classes, okay? So let's do a simple proof, okay? The proof looks like this, right? So firstly, delta ij is called a Kronecker delta, okay? In machine learning, indicator variable I means that if this condition is true, it's 1, otherwise it's 0. Kronecker delta means if I equal to j, your delta is 1, okay? If I is not equal to j, your delta is 0, okay? So put simply, this is basically, there are two cases, okay? So if, I equal to j, right? So we just write it I, right? Y take partial derivative AI. In that case, this is 1. So this is y 1 minus y, okay? Maybe yi. Okay. So this proof is very similar to previous one, right? We have I 1 minus y. The other case is actually when I and j are not equal. In that case, we are saying that this is y times 0 minus 1 network. So this is the, it's a negative yi yj, okay? So there are two terms. We will prove each individually, and then collectively we have this, okay? Let's first consider the case, because here we have enough space. We don't need Wi-Fi, okay? First, let's consider the first case, right? So that I is not equal to j, okay? I is not equal to j. In this case, firstly, what is y, right? We need to write out y. yi is something like this. So yi is exponential ai, okay? This is exponential, maybe a1 plus blah, 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 plus e aj plus e a k class, okay? So you can see that this, if your I not equal to j and you take derivative j, so this is a constant to you, okay? Because it's ai, it's not aj, right? So so the only term that relevant to you matters to you is aj here, okay? And so now let's take a derivative of this term to aj, okay? How to do that? Right. So basically this you can see the term down there, okay? The term down there is firstly you treat this as, let's say, u, okay? And this is basically a constant you write at the beginning, and then this is one by u, right? So if take a derivative, so 1 u square, okay? Negative u square. Then we take a u, derivative u to aj, right? So, u is what? The other term is relevant to aj, okay? Only one term, which is e aj, is relevant to aj, right? E aj, take derivative aj is e aj itself, okay? For simply, what we have is something like this, right? So if you look at this term, it's negative u square. U square is this summation, okay? Summation I, e ai. It's summation square, okay? The term is ai aj, ai aj, okay? Let me, because I'm kind of run out of space. So let's keep this conclusion and then let's come back, okay? So what we show is that if I is not equal to j, then the derivative yi derivative aj is equal to summation square, summation square, two summations, okay? So ai times aj, okay? So what is this? Right. Following this definition, this is y, okay? Oh, there's a negative sign, I forgot to put, okay? What is this? This is yj, okay? So this is really equal to negative yi by j. Okay? Keep in mind when this is not equal, this is 0. So this proves this case here. Okay. Any questions?
Yes, Professor. So if we are summing the denominators, how would you know you're doing the differentiation with respect to that class?
I don't understand your question. So let me try to answer your question a little bit, okay? So our derivation actually is doing this, okay? So we are doing y, okay? So yi is equal to, following this definition, exponential ai, okay? This is exponential maybe a1 plus exponential a2 plus exponential ai plus exponential aj plus exponential ak, okay? We are taking derivative aj. Okay, only this term matters. The others are constant. You can treat them as b, b2, b3. It's okay?
I understand. I'm saying if we are adding them, how are you isolating aj term, right? If we add them, it just becomes one term. We just need the aj term at the bottom, right?
So you treat this term as u. Is this okay?
Okay.
This term as a constant b. So when I take derivative, it's b, and then u is negative 1, right? Take derivative of this negative u, negative 2. It's okay?
Okay.
Then follow chain rule, then you take derivative to aj. It's okay?
Yes.
This is a summation, take derivative 1 minus u, okay? It's derivative. Then this u is a summation of this term. It's okay?
Okay, so I kind of understand that you're using chain rule to.
Yeah, exactly. Okay. Yeah, so this constant, the first move to here at the beginning, right? And then this term is in u, okay? This is 1 minus u. Okay, take a derivative of negative u to the power of negative 2, okay?
I
you
see.
need to familiarize yourself with calculus. After that, then the chain rule is now taking this as a u, take a derivative aj, okay? The others doesn't matter. It's ex, take a derivative x is ex itself. It's okay? That's what we are doing.
I understand that. I understand that.
Yeah.
Okay. I have a question.
Okay. Yeah.
Here, if you change yi, if you write yj, then only the numerator is changed, right? Denominator remains as it is.
Can you repeat your question? I don't get what you said.
Yeah, first line of this page, here yi you have the value of yi, right? And if you write yj, then only numerator change, right?
Where we write to yj? This is yj, right?
It's first line. If statement.
Yeah, if statement. What's the problem?
If you write there yj, if you write yj there.
We are talking about this j here, right? Okay, so this is what I want to say. Okay, so.
Okay, yeah. If you write here j.
This j doesn't matter. You can use anything, a, b, l. It's just saying that we iterate through all of them. It's a expansion a1 plus etc. to expansion ak. It's okay? This is a script for this. You can use anything.
My question is, if you write in place of y, if you write yj, only here is change, right? Only change is here. This remains as it is.
You mean change this to j, right?
If you replace I by j.
Yeah, exactly. Because this j you can replace anything.
And
yeah, right. So we need a notation for this to iterate through them. That's all we need. You can use L or something. Okay. So this is for any I. Okay, you can call it j also. That's okay. Right. So this is the first case. The second case. So here this j doesn't matter, but when we take a particular j, Z master. Okay. This is a particular class j. Okay. And so the second case is really, so if you think this is confusion, let's write it as maybe L, okay? So just to treat this as L, don't confuse with this j. And the second case is I equal to j, okay? I equal to j, then in this case, what you have is this, right? So yi divided by ai, okay? And this is equal to basically, first, what is y, right? So this is exponential ai, and a bunch of constant, right, plus eai. plus a bunch of things. Okay, so this can be, take derivative. You can think about it as two parts. Firstly, this is if, right? This is G. One divided by this is G. Right? First, it's a f prime G equal to what? F prime is still AI. Okay, and the G is still divided by the summation. Okay, next term is f G prime. Right? F G prime is what? F is a constant now. Okay, so and the G is you are taking derivatives. Right? So firstly, you treat this 1 divided by U as, so this is the 1 by U squared. Okay. Then you take this, take derivative AI. Okay. So it's EAI again, just like before. Right. So put simply, these two things should be summed together. Okay. This summation is U. Okay. So put simply, let's see where we have space. Let me see. So this is EAI divided by the summation plus, so or minus summation square, okay, EAI square, okay, and this you can write it out like if you think about this as square, right? So this is a timing summation at both bottom and top, right? So let me see. I think how to write it out. So I think it's a little bit not easy to see. Let's just keep in mind that the bottom is already the summation square. The top is the EAI times summation minus EAI square. Okay, let's clear this page. Now the bottom is the summation square. Okay, so the top is EAI times the summation minus EAI times EAI. So times EAI. So you can put it like this. Okay. So this basically, if you write them out, you can treat them as summation of this times summation of this. Okay. Right. So summation of this is basically y. Okay. This term is basically this divided by is 1. Right? 1 minus y. Okay. This gives you the other case. Any questions? Yeah, so you can put this offline and do some practice of maybe, I think the calculus, maybe for first year college students. Okay, so yeah, let's continue. And so, because you may forget it, right? So you can repeat this yourself and try to refresh your mind a bit if you want, okay? You can also just remember the conclusion. Yeah, so this is a reminder of attendance. We will finish this. Let me see how many pages. We will finish maybe 1 or 2 more pages and we'll stop, okay? And so now the update function looks like this, right? So let me see. So this derivation is just like before, okay? So if you remember previously, we have something something complicated, right? So we have 2 parts that are merged to 1 part, right? Here we are also merging to 1 part, just following the same rule, but just previously, this is 1 minus y. Now this 1 is represented delta ij. Okay, we will not do that derivation again. Okay, but we can show that derivation somewhere already, just to assure mind. It's 37. I think it's here. Okay. Yeah, so merge these 2 parts, okay, into 1 part. Okay, so we can do the same thing here. Okay, so let me see. 37. Okay. So just the 1 minus y now becomes delta minus y. Okay, and now just follow the the multinomial function. You will get this. Okay. Now we can write them out into 2 terms. One is summation of this, which is this. Right? So base have subscript I. Another is summation times this. Okay. But this This has no subscript I. You can take it as a constant take out. Okay. And now let's take a look at these two terms, right? So this term is actually R. Okay, because this is what? This is a Kronecker delta, which means for I1, so this iterates through all I, right? So there's a delta 1j, delta 2j, delta jj, okay, and there's a delta kj. Delta jj is 1, the other is 0, okay? But you sum them up, it will be 1, okay? So there's a coefficient is, so it's only for the j's term, this is 1, and the corresponding coefficient is j, right? So this is why this term is rj, okay? And look at this term, the summation of this column is 1, right? So this is why this is yj, okay? So this conclusion is actually, the nice thing about this conclusion is this is exactly the same as before, okay? Like we'll see before, right? This R is taken from the log, okay? So R divided by Y, right? So, and then this is merging these two terms, cancel, and then finally we have this all the way to here. I will leave the detailed derivation to you guys, okay? So, any questions?
Yeah. The last bit. So the L iterator, is that iterating through the different features and having,
no. Here are the meanings. Okay, your iterators is always through the data items. It's a first row, it's a second row. Okay.
Oh, okay.
That's why we have L and we have parentheses, not to confuse with. So this is the first row's features. Okay. This is,
okay.
And
so X is.
Yeah, X
like
is
the vector of features.
Yeah, the table's row. Okay.
Got it.
Yeah, there's a particular column you see. Okay. And this, let me see what the others. This I is because we have K classes, right? So that's why we have this R. Okay, multiple classes. Okay. This J is WJ, right? So this W1, X1, W2. So this is basically the dimension D. Okay, this is which dimension, right? So J is how many columns in the table. That's the superscript of the table. Okay. The I is how many classes you have, C1, C2, C3. Okay, this is. Okay. And finally, the L is which row. It's the first row, the second row. Okay. Yeah, again, so there are a lot of notations, so you need to work out yourself again and maybe summarize for this. Okay. But again, so yeah, it will take time to be comfortable, right? So we cannot wait. Okay, so different students have different speed.
Hi, Professor. I have a question. So what's the mean the delta before the WG?
Where's WG? WJ, right?
The delta WG. What does it mean?
Oh,
yes,
delta is this. So if you look at here, let me go to the previous page. Delta is the step length, learning rate. Is okay. Maybe go to the previous page, it will be clear. So this is a derivative, okay? But when we do gradient descent, derivative is where you increase your speed most, but we want to minimize the error, right? So we need to have a negation, okay? And then we have a step length, okay? Although this is deeper, you should have a bigger step. This is slower, you should have a small step. But how large a step is defined by the lambda. It's okay? So delta is negative lambda times the derivative. It's okay? Yeah, if you are not answering, I assume it's okay. Right. This is basically following the definition of gradient descent. Negative gradient direction with a step length. Okay. In general, there are a lot of variations, right? So for example, the step length can decrease, right? So with iterations, okay. So, but here we are having a fixed step length. Okay. So basically, it's a derivative with some constant negative length.
I have a question.
Okay.
Doctor.
Yeah.
The delta, in delta, why you multiply by eta? Delta is the gradient, right? Only derivative.
Let's take a picture here, okay? So for example, if we are at this point, okay? Right, and the derivative will be, maybe this is rising faster than the other side, okay? So derivative will be this direction, okay? Right, so what we should go is negative gradient will bring you close to the slower point. So this should be negative, okay? The gradient is this value, negative gradient is this factor, right? And we should scale it in some way. So the scale of this is lambda. This is called the learning rate, okay? This is basically gradient descent is saying that your W, next time you change the W, the change W is basically W equal to W plus delta, okay? Or for each W, okay? This should change along the negative increasing side so that you will decrease the error function, okay? And the rate of decreasing is defined by that. It's okay?
Okay.
Yeah, probably you are not familiar with gradient descent. I also didn't explain this before. So yeah, but this is intuition. Okay, so your gradient is increasing. So you want to decrease, find the minimal here, you should decrease, okay? And then you need to say how fast you want to go, right? Maybe 1 step here, 2 steps here, 3 steps here, right? If your lambda too small, you will go very slow, okay? Yeah, so that's
Professor,
yeah.
Professor, I have a question here.
Okay.
I understand that the gradient represents the slope of the rise direction.
Yeah.
Can you also give a same intuition for the Hessian also, Hessian matrix, I mean representation? Why I'm asking is that the gradient represents a vector in the rising direction. We are moving in the negative direction of the gradient. In the same way, is the Hessian having any other representation like this?
What representation? I don't quite get your question.
I mean, you have what you just illustrated is that gradient is pointing towards the highest slope of the counter, right? And we are moving to the opposite of the gradient.
Yes.
So, similar manner, can you give an interpretation for Hessian?
Oh,
in the similar manner.
Hessian is a curvature. Okay, it's a curvature. In 2-dimensional curvature. Okay, so yeah, it's difficult to give you the intuition. So it's a Hessian is convex, right? If you are curving like this, it's convex. If this is like this, it's concave. Okay, if you are in 2-dimensional space, it's whether it's a bow shape or downwards bow shape. Okay, and in between concave and convex, it's a flat. Okay, it's a flat hyperplane. Okay, this may be the intuition. It's okay. If this point the Hessian is 0, then it's flat. Okay, if the Hessian is positive, it's bent upwards. Okay, if it's negative, it's bent downwards. Okay, if it's a very large Hessian, it's bent a lot upwards. It's a curvature. Okay, that's all I can say. It's okay.
I mean, taking double derivative indicates that if the double derivative is 0 and it's positive, then we have reached to local minimum, global minima. That's what interpretation is, right?
Oh, it's something like this. Okay, so if you your let me see just one. Okay. Yeah, let's use an earlier slides. That may give you some better idea. Okay. Let me see. Can you see this?
Yes, Professor.
Yeah. So basically, let's say if this is the convex function, right? So then the Hessian every point is bent upwards. Okay, bent upwards. Then you put a ball and it will do gradient descent. It will reach the minimum point. Okay, right. If it's concave, you do gradient ascent. Okay, so you don't have negative sign. It's just a step less times the gradient. You will reach the max value. Okay. So this is curvature, right? So if you look at the curvature here, along one side, this is 0. Right? So along the other side, it's positive, right? So look at here, the curvature, it's some are negative, some are positive, right? So on this point, it's going to be flat, it's 0. So this is the idea, okay? So if you put a ball here,
point.
it will not, if it reach here, it's not minimal, right? You can continue here, right? Only when it's a convex, you have the guarantee it's minimal. Okay, only when it's concave, you have a guarantee it's max, okay? Otherwise, you cannot guarantee that, okay? But you don't have to, this convex is a strict requirement, right? So you can say this is the convex, right? So you can also have this, right? So you still get a minimum, okay? Right? You look at Gaussian distribution, right? You know that the mean is max, right? But you know it's neither convex nor concave, okay? It's okay?
Yes, Professor, got it.
Yeah, I hope this will give you the intuition. Right, so maybe this is better. Yeah, let me see. Again, so just to remember some conclusion, right? So the Hessian is a positive semi-definite, okay, which is a matrix positive, right? So then it's convex, okay. Let me see where the slides. Yeah, let's see whether we want to take a break or we continue. Okay, let me see how many slides are there. Let's finish this, okay, and then let's continue. All right. Yeah, so basically, so this is one derivation, right? So and so if this is Wj, right? If you have W0, then the corresponding term is 1, right? So you have this the other case, okay? Right, so this is implementation of the graded set. Okay, so just one for loop to compute OI is just A here, right? So and you compute the summation and then you put along the negative sign, okay? But here, after taking negative, this is actually positive. Therefore, you have pluses. Okay, what we are talking about this, right? So this delta is already taking negative of the gradient, which gives it positive. The plus is delta. Okay, so you have plus this delta. But in order to compute this delta, you need to compute y. Y, is negative of a summation. So the summation is computed by this for you. Okay, 1 to k. So you can look at the details later. Right, so this is taking softmax. And here are the examples. So you have 3 classes. Okay, so and if you look at the this is PDF. Right? So this, let me see how to interpret this. Yeah, so this is the gradient. So this is the error function. Okay, this is the error function. This is the discriminant function G. Okay. And if you look at the probability, it's kind of reverse of that, right? So it's like if you on this corner you are very likely circle. Okay, on the other corner it's very likely, but in the middle it's very uncertain. It could be equal to 2 classes. Okay, probably equal to 2 classes. And in general, we can go beyond a linear function for the logic. Okay, the logic can be a quadratic function here, right? And and you can also have the features, be a linear function, but the features are the basis functions, right? It could be sine x, right? So x1, x1, x2, etc., x1 squares, right? So you can make a more complicated logistic regression functions, okay? But in general, we don't go with these because there's no convexity guarantee, right? If you want to do this, why not just go to XVM, okay? So usually we use the SVM or we use a generalized linear model, okay? So this is more like a generalized linear model, right? So, but GLM, we're directly using that model, okay? And the basis function is also relevant to the hidden units in neural network, right? So you have the signal change to a middle layer signal that may be totally different from your input, maybe high level features, okay? So this is a hidden unit. It's like doing some basis function transformation of the original feature, okay? And also for kernels in the supervised machine, okay? So we have 2 kernels. We will see that in later lectures. One is the kernel density estimation. One is the supervised machine's kernel methods. Okay, they are 2 different kernels. Okay, just using the same name. Don't get confused about it. And so finally, is about assignment 1. Last time I want to talk about this, but it takes some time. So yeah, so basically you need to know how to take gradient, right? So what is maximum likely estimation, right? What is logistic regression loss, right? So loss is just the cross entropy loss error, okay? Obtained from the the Bernoulli or multinomial distributions likelihood function, okay? After you take a negative log likelihood, you get the loss function, you get the cross entropy error. And the base estimation was prior, right? So we have a question asking about prior. Okay, so you need the prior and to time with a class conditional probability. Okay, and so one question, particular question, is about vector calculus to derive the, linear, I think least squares, right? So least squares method. Okay. We have seen that in the class, something like D transpose times D, right? So very complicated. If you use a vector calculus that we will go through in the next few slides, it will be simple, okay, a few lines. So that shows you that when you know vector calculus, it's totally on a different level of thinking, okay, than if you think element-wise in matrix, right? And then is convexity, right? So convexity is basically, you want to prove that Hessian matrix is positive semi-definite, okay? Right, you need to know what is Hessian matrix and how to compute it. Finally, Newton's method. Newton's method is relevant to this assignment, last question. But this time, we only let you look at a scalar function, right? So the x is a scalar, not vector. So that's super simple. You can easily understand it, okay? But it's generalized to something more complicated on high-dimensional space, right? So in high-dimensional space, instead of, if you remember in gradient descent, you have a negative step length times your gradient, okay? Right. So in Newton's method, it's still times this vector, okay? Right. So, but this is the inverse matrix of your Hessian matrix, okay? This is Hessian matrix inverse, right? So this is different one here, right? So this is a value times a vector, okay? It's a vector, right? This is a matrix times a vector. It's still a vector, okay? Keep in mind a matrix times a vector or a row times a matrix give a row matrix, okay? It's a matrix times a column gives a column. Okay? So that's slightly different, okay? But you can show that if you use this to compute, because now you use more information, right? You compute a Hessian, right? And if your function is, convex, okay? If your function is truly convex, this is much faster. Maybe the other will take 10,000 iterations. This only takes 3 iterations, okay? Because you have a better fitting of your direction. You know that the curve will bend up here, you will reach here directly instead of small steps. So there's a derivation here, but keeps these conclusion in mind. And to get intuition, you just look at the last question in the assignment 1, in the scalar case. You generalize to the high dimension case, okay? And so this is the update. This is the gradient column vector you get, right? W1, W2, W0, right? So, and this is the Hessian of the W matrix in largest regression, okay? And you take inverse of the matrix, which is still matrix times column, okay? This you will implement in the next assignment, right? And the vector calculus, so this is just telling you the definition of Hessian matrix. The ijth element is Wi, Wj, okay? So you know how to take a scalar, to 2 variables partial derivative, then you can compute the Hessian matrix, okay? So just remember the conclusion form, okay? And this is the one-dimensional vector calculus, right? So this is ax, take derivative x is a, right? So, but you need to have the transpose because it's an inner product. And this is the quadratic function ax squared in some way, right? So if you take a derivative, this is ax plus a transpose x, okay? In some way, right? So if it's a quadratic, it's a symmetric matrix, a transpose equal to a, then it's a 2ax, okay? And finally, the concept of, let's say, what is the PSD, right? What is positive semi-definite? PSD, okay? So let's say your Hessian matrix wants you to prove its PSD. You just prove for any vector x, right? Like our V that we derived earlier. You have V transpose times A times V. It's always larger than 0 or equal to 0, okay? So this is what we have seen in the beginning of the class, that we basically tell you the solution, okay? If you can prove this for any V, right? Then the Hessian matrix positive semi-definite, then it's a convex function, okay? Right. Why it's convex and you can reach the optimal, right? So if you are interested, you can look at the convex formalization, right? So, but I would not recommend you to do that because, you are not doing mathematics, right? So even, you know the function ax squared, right? Is of this shape. It's because, maybe 1,000 years ago, people just try what is a different value of x and see that from y and make a curve, right? Now you carve this in mind. You should also carve this high dimensional quadratic function in mind. Okay, this is what you need to remember. Okay, even if you prove to do a lot of things, if you don't remember it, it's wasting the time. Okay, maybe you will forget it quickly. And next time, go back to those low-level details again. Right.
I have a question here.
Okay.
Just I wanted to reinforce the takeaway. If a matrix A is positive semi-definite or positive definite, then it's called Hessian, where we can find the where the function is going to be based on that function, we can get to the global minima. Otherwise, we won't get to global minima. That's what Hessian
Yeah,
says.
you are almost there, but here we are just for any matrix, what it means by PSD. If you specify this is a PSD. In the optimization case, if your target function, right, your target function divided by your parameters that you want to optimize, if this this guy's target, this if this is a Hessian matrix, right? If you put Hessian matrix into A, then this means this loss function is convex. Okay, you will get a global minimum. Is it okay?
Okay, Professor. And I have a follow-up question as well.
Okay.
To reach the global minima, there is no, I mean, we can use multiple optimizers like right gradient descent, Adams, many other. I mean, we can use multiple optimizers, right?
It depends, right? So for Hessian method, so there are three solutions. The first solution directly take a W1, W2, W3, take it to 0. If you can compute exactly those W formulas, that's the optimum. It's okay if you can prove it's convex. But sometimes you cannot analytically solve it because you don't know how to solve the equation, right? And then you have to do gradient descent to get close to it, okay? Right. And if this function is again convex, then you can use the Hessian matrix you can compute, then you can quickly go to here, right? If it's not convex, you can only do that in very good curvature places, maybe very close to your global optimum. Okay, otherwise you will stuck somewhere, right? So if you have a concave place, then the Hessian is negative, you will pull you away from the optimal place. Okay, so you can first do gradient descent and very close to your Hessian. This is fine. Okay, so there are different ways. Yeah. But in our case, because we just have the convex function, right? Wherever you are, you will always reach the optimal. Okay, in the latest regression case, so we will ask you to implement Hessian, the Newton method. Okay, it will always succeed unless your implementation wrong. Okay, also gradient descent will always succeed.
Thank you, Professor. Nice explanation.
Yeah, you're welcome. So this is basically high-dimensional conclusion, generalization of one-dimensional case. Okay. Yeah, any questions? So I think that's the last slide. Okay, this is basically helping you to grasp this assignment. I think now, after today, you should be able to do your assignment. Okay, and yeah, so let's take maybe 10-minute break. Okay, in 45 we'll come back and take attendance. Okay, then we'll continue with the next lecture. Okay. Or maybe we'll briefly go through the final project first. Okay. Yeah, we'll go through the final project after 10 minutes. Okay.
Can I ask a question?
Yes.
With the final project, what about groups that don't have up to 4 members in the group? Would they be graded same way as the people with the 4 members?
Oh, actually, we encourage teaming. So if you select our project, then we probably will grade the same way, but we will scale down the requirement. For example, if we have 4 students, we will ask you to really do an advanced project. So in this project, basically, we will tell you that there's some additional stuff you can do. Okay, if you have 4 students, for example, in the group, we really want you to do to get 100 marks, you need to do the second part. But if you are only doing it alone, maybe the first part is finished, that's also fine. Okay. We will start to consider that, but we will not. That will be not a major factor. Okay. So basically, our final project will have one specified topic. Maybe we'll add some other topics later. Okay. So, but this time we will take a specified topic. Okay. So because the department basically encourages that because some of the students reuse the project in many courses. Okay. Right. We want to avoid the possibility that other course projects will be reused in this course. Okay.
I have a question.
Yeah.
You said that the single person also can do the project. What about the single person? How much tax they have to do if there is no group?
Yeah, a single person can do the project. You can just say, hey, I cannot find any teammate. I want to do it alone. That's fine. Okay. You don't have to have a group. So our only requirement, as said in the syllabus, is that you cannot have a group of more than 4 people, right? This is what I want to avoid. Let's say 20 students just do one project, right? It's unreasonable. Okay. So if you can have up to 4 students together, right? And so yeah, so that's what I want to say. I will go through the project shortly.
Okay.
Okay, so let's begin. So for this final project, we would so the best way to avoid reusing some other cost project to use a new data set, right? So remember that. Oh, sorry. So why there's a step by step? It's okay. So remember that you have a via annotation, right? So VGG image annotator, right? Annotation assignment in the first mini project, right? So we have selected high quality annotated images along with their annotations, okay? And then we assemble them into a data set, and we will distribute them to you guys. You can download freely, okay? And then you will use that data set to complete that assignment, okay? Yeah, so for this assignment, it will be slightly difficult because it's a final project, okay? But you can treat most of the things as a black box, okay? The model, like we will be using a, image related model, but most of the model can be treated as a black box. What you care about is really the loss function, right? So we talked about loss function a lot, like softmax, cross entropy loss, etc. Okay. I think some student just plot something. Let me see. Right, so, and let me see. So you care about the loss function and a few of the major, like how to evaluate the model, right? And what is the classification regression, right, for the loss function, okay? These concepts are basic concepts that you need to get familiarized with, and then you will be able to Google stuff, right? So for example, you Google a blog talking about how to use that model, right? What's the input, what's the output, and be able to handle a complicated machine learning model that maybe we haven't covered that, but because you know the basic machine learning concepts and you have the hands-on ability to complete a more complete model than just calling scikit-learn, okay? So it actually not difficult because you can easily find a blog and follow that step by step and work on our data, okay? But that will not give you a full mark, right? So maybe for one student it's fine, but if you have a group project, then we do have a little bit more demanding. We will talk about that at the end of this this solution. Okay. And so, by the way, for grouping, the TA office hours, right? So the TA hours, basically we configure them as chat room from now on. Okay, so you can just go there, and it will be a big chat room, and you can go to so-called breakout room if you want to chat privately with a couple of others. Let's say you can discuss and find, hey, maybe you have common interest, right? You find an empty chat, breakout room and chat, okay? For TA, it will be in the first breakout room, okay? Basically, the other places you can just chat freely and forming groups. This is maybe a way that we can facilitate the discussion, okay? You can just chat there, right? So freely, and because the TA is not at the main lobby room, right? So he's at the breakout room, okay? One at a time to the TA's room, otherwise you can chat freely, okay? And try to form in groups. And the requirement of this project are as follows, okay? Firstly, you will select a state-of-the-art object detection model from our provided list. Okay, so we will provide the 3 models that you can choose from. Of course, you can try other models. Okay, just let me know, then you can try. Okay, and I think there are way more models than that. Okay, so we can take a look at some examples. Right. So,
Professor?
Yeah.
So I already discussed Gopi about a project idea, and he approved. So
Sure,
this
yeah.
doesn't
So
apply.
you can discuss freely with Gopi, and if he approves, and then for all the students, fine. Okay, yeah, don't need to discuss with me. Okay, yeah. So let me browse this. Okay, so in general, these days, scikit-learn is really not enough. Okay, but because we are teaching just the basic machine learning. Okay, so we cannot cover too many advanced models, right? So actually, if you go to this website called paperwithcodes.com, the SOTA is state of the art. Okay, and there are all kinds of models like computer vision. If we are particularly go to the object detection. Okay, and there are a lot of papers, a lot of models, right? And these papers and with code. Okay, so you can use any of them if you think that's interesting. You can let me know, and I will approve it, right? So for example, then like using the MobileNet, SpineNet, etc. Right? So there are so many papers. Okay, so that's kind of crazy. But in particular, we will suggest you to use 3 models that we are talking here, unless you want to try others out. Okay, you just let me know, right? And there's also medical imaging, right? So brain tumor, etc. Okay, so and natural language transformer models, attention models, etc. Okay, and a lot of graph neural networks. Okay, so time series predictions, knowledge base, knowledge graph, etc. Okay, and there's a lot of models. Okay, so these days, right. So in general, if you are interested in doing deep learning model research, right? So you have to understand the TensorFlow, for example, right? So maybe we don't have time to teach that. And in deep learning, I know that previously the instructor briefly covered that. That's also not sufficient. So you need to self-study that also. Okay. So I have a bunch of students studying with me this year as a practice, like those kind of tweet geolocation prediction, and and also some neural networks. And I think it's pretty successful, like a prediction, finance data, etc. Okay, so basically, if you have interest, you can contact me, right? So we will give you some training on TensorFlow, maybe reading some materials, and then work on a project, some research. Okay, and usually, student working with me is like 2 months if you are smart, you quick learner, and you have sufficient time to work on the project. Okay, like a summer direct reading course, or a thesis track of the master program. Okay, or if you are a PhD student, like in some research project you are using those kind of models, you can let me know. Okay, so I can see whether I can help or have time to do. Okay, and
So
yeah,
if we choose if we decide to choose our own project, does that mean we can use any library at all, like TensorFlow?
yeah, you can do that. You can do that because we are teaching just a basic model. Okay, we are not requiring to innovate the model, but you need to use a state-of-the-art model. Okay, let's say if there's a better model here, but you are using some primitive model, right? Then that's not good. Okay, because for what we teach you, the current model without deep learning can only work with relational tables, right? So the kind of rows and columns tables, right? And we cannot really working with images, natural language, etc. Right? That will need deep learning. Okay. So you are,
so any deep learning framework is considered state of the art, I would think. Is that right?
Yeah, any problem. Basically, I show you a web page, right? So before, right? So if you want to do something else, just let me know. I will approve that. Okay. So sorry. Let me see. So let me copy that link here. If you are interested in any particular topic here, right? So just let me know. Okay, you can explore. But there's only 1 month, right? So you want to find a balance. Maybe it's better if you want to explore later, right? So there's reinforced learning, StarCraft, right? So I know there's people doing game deep learning, right? So AI, right? Game AI. Okay, so if you are interested in a particular topic, you can discuss with me, but you need to understand the timeline, right? So we only have maybe a little bit more than 1 month. Whether you can handle that, you need to think about it. Okay.
Okay, so this website, I was actually thinking this website is where you go to look at different kind of models and libraries out there. So
yeah,
you saying you can actually go to this website and choose or look at
your call, your decision, right? So this is just an example that there are different branches of machine learning and deep learning that you can explore, right? So if you want to follow this website for a particular model, right? So that's fine. Okay. You can do that. Or you have other, like your advisor or some like you are involved in a company, some project. That's also fine. Okay. So we don't have specific requirement, but that cannot be just a simple pandas load a CSV file and then call a secular model and then show some like a precision recall, etc. Okay. And then do some visualization of the confusion matrix. That's too simple. Okay. One afternoon you can finish that. Right. we want you to be able to work on complicated stuff, right? Using what you learned here. So we are teaching two kind of things, right? So we emphasize two things, right? One is the mathematics, right? So that is important if you want to do novel models like in ICML and NIPS, right? So in CVPR, etc. Okay. Another important thing is that you know these small details. You at least even you scikit-learn. You are not just calling the model and it just fit and predict, right? You know the model has some strengths and weaknesses, right? So for this, they have some properties. We cannot use this model. We should use that model that may be better, right? So this is one thing that we want to teach you, okay? And the second is you know how to configure the hyperparameters, right? So previously you blindly use it. You don't care about so many parameters in the model, okay? Now you will be able to use it if you are a user, not a researcher, right? So, and on the other hand, we also want you to have a end-to-end path of the hands-on process, like annotation file, find a model, and address the model on the data, right? So you know how to find where to find the best model. And basically you need to handle the input side and output side, right? Especially the loss function side. Otherwise, the internal model complications, you can ignore them. As long as you know how to, this is a regression function, this is a classification, right? So you need to understand these general machine learning ideas and how to do this model, how to evaluate in that particular domain, right? So that's the capability we try to let you work on the final project, okay? And because of the, let's take attendance first, okay? Because it's reminded me a lot of times. Okay, so I will sample some students. And probably we just have time to go through the final project. We will continue with the next lecture next time, okay? And let me see. Let me just sample some, okay? Bhavana? Bhavana, are you here? Are you here? Sunshine? Sunshine down?
Yes.
Okay. Muhammad Harris? Muhammad?
Yes, I'm here.
Okay. Annie?
I'm here.
Okay. Nishant? Nishant? Nishant Paba? No. Let's run this. Nancy? Nancy? Nancy?
She just responded in chat that she's here.
Oh, I see. Okay. Let's scroll up for two more people. Okay. Manoj. Manoj.
Yes, sir.
Okay. Chun Yao. Chun Yao Chen.
Here, I'm here.
Okay. Mingyong Liu.
Yeah, I'm here.
Okay. Chad. Chad Muchis.
I'm here.
Okay. Yeah. Okay. That's for today attendance. Okay.
Professor?
Yeah.
I just got a call from Bhavna. She got disconnected and she's trying to connect back.
Okay. Let me see. If he's back, let her send me a message in chat. Okay.
Okay.
Yeah, I can send it back. Okay. And yeah, let's continue. And yeah, so the requirement is that you select a state-of-the-art object detection model, right? Maybe on the GitHub there will be a code, okay? Preferably from our provided list, but you can choose another model that's newer and maybe for some better reasons, maybe it's faster, like the MobileNet. Obviously, it's for faster training on mobile devices, right? So, and okay, also you can use other models like object tracking, right? There are some models for object tracking, etc., which is more recent, okay? And you will use the object detection model on our drone data, right? We cannot do tracking because we are not a video, right? So that's why we choose the object detection model on our drone data, okay? And then you will briefly introduce in your report, right? So how you customize the model, right? And change the loss function to our classes, etc. Okay. So let me see. Bhavana. Okay. So Bhavana, can you remind me at the end of this course? Okay. So I make sure you are all here. Okay. Right. Then at the end of the course, just send me another message. Okay. And then you will report some metrics, right? That's, for example, for object detection, right? So you will have the average precision, mean average precision as a metric. You want to learn a particular metric for that particular domain, right? Or maybe for natural languages, there's something like a blue score or something, right? So you need to self-study, have the ability to self-study how to evaluate something, right? So I think even in scikit-learn, there's the average precision in metrics, okay? And then you will show the 10 best detection results, right? Visually show, and to show that your model is working, okay? Right. So you numerically you show it's working, so you the precision, and also you show that they detect something, okay? So we will rank based on this list, okay? Give you the marks.
So Professor,
yeah.
So if you mean state of art, like let's just say for object detection, I know YOLO is the latest one and most advanced. So are you asking us to implement it on a particular data set, or how does it work? Like
yes, the model is all online. Okay, you just follow their instructions and you can use it. Okay, we don't require to implement it. Okay, yeah. So you
got it, Professor. Thank you.
Okay, so because we haven't talked about convolution now, right? So you will not be able to implement the middle layers. Okay, you need to know how to work with the input, right, and the output. How can you configure it, right? And yeah.
Got it, Professor. Got it. Thank you. So I believe you're looking for a complete model implementation pipeline.
Yeah, exactly. So you will be able to handle this, right? So let's say later after graduate, your boss said, "Hey, I want to detect that thing," right? So you annotated some and you train the model. It's an existing model. It's not new model you propose, right?
Okay, and can you also tell us how the individual evaluation is done, like project evaluation?
Individual evaluation, basically, you mean the marks?
Per project, yeah.
Marking scheme, right? So yeah, basically each point will be 20%, but we will have to check how the other students work to do comparative marking. Okay, for example, if your fine tuning is correct, but the result is always very bad, then probably you get this 20%, but you will not get 4 mark here, right? So you need to do some trick to improve it, right? Or fine tune the parameters, etc. Okay, we'll talk about this in later slide. Is okay?
Yeah, sure.
In general,
and
like
one last question, Professor.
Yeah, if you in your report you finish each part correspondingly, each is maybe 20 points. Okay. Yeah. What's the question?
So what other topics can we select? Here you have mentioned object detection in particular. So what other topics can we select?
So in our drone data, you have the objects and you have the bounding boxes, right? So you have the masks. So you can only do object detection in this model, right? So if you want to select another project, you have to use another data set, and you need to get my approval. If I think that's interesting, you can work on it. Okay. And the reason we want to use our data set is because we don't want you to reuse some other projects, maybe in your old projects or in another course, right? So we want to avoid that. It's okay. Yeah, another point is, allow you to do a end-to-end model pipeline. Okay, machine learning pipeline. Yeah.
Yeah, thanks, Professor.
You're welcome. Okay, so for the object detection models, there are 4 concepts, right? So classification, just give an image. This you say whether it's cat or dog, right? So localization is saying not only this cat, but also where is this cat, right? You have the bounding box for it. Okay, and the object detection compared with the localization is that you have multiple objects. Okay, so you have so many objects, you want to detect each of them using bounding box, right? And our annotation is actually more sophisticated. Okay, so we have all the pixels, right? So right? So this is a segmentation. Okay, each object, these pixels are from this object, right? We have a polygon. Okay, and if you want to work on just bounding box, you can take the bounding box of those polygon points, right? So then you get the bounding box, and you can work with those models that only take bounding boxes. And so all the detection models are based on the localization models. Okay, so localization models are kind of something like this, right? So you have some convolution net, you don't care about what's in the middle, right? You know that the input is an image, right? In our machine learning model, it's a bunch of lines, right? So in deep learning, it's a bunch of images, okay? And there's a mini batch concept we'll teach in the next class, okay? Because today maybe we don't have time, okay? A mini batch of rows in regular machine learning model, in this kind of deep learning model for computer vision, you have a set of images, a mini batch of images. Okay, and the output, for example, is a fully connected layer, right? So this is the last layer features. Okay, and then this layer features is more like our role. Okay, for basically we are saying that now you have an image. Okay, and then you use some complicated models, you extract it. Then what you get is x1, x2, x3, etc., xd. Okay, now the rest is what we learn. Okay, so basically you don't care about this part, just use the state of art here, right? Now for each data object, you extract the features. The rest of those features are relevant to what we teach here. Okay, this is more like a table row, right? So these are high-level features, like whether this is an animal, whether it's a tipped ear, right? So round eye, etc. Whether the length of the leg, etc. You can think about it like this. Okay, even though it may not be so meaningful, right? So okay. And once you have this row that corresponds to this, it's called embedding, correspond to this data item, right? And this row are the features. Then you can build a, let's say a fully connected layer, which we'll teach next time. Basically a bunch of, logistic regression models, okay? Right, so one logistic regression for cat, one regression dog, for example, one regression car, okay? And then you will have a softmax over this, right? So softmax will teach here, right? And this is for classification loss, okay? And in the meanwhile, you also care about the location, right? So the location is basically x1, x2, y1, y2, okay? So these are 4 numbers, okay? These 4 numbers, this is width and height, okay? These 4 numbers are numerical values. So you have the regression, okay? And you will have the regression loss, okay? Like mean square error, okay? And these, both of the loss, you want to minimize them, right? You want the box to be accurate, and you also want to guess what's in the box correctly. It's not a dog, it's a cat, okay? And then you just do the training, okay, fit in some way, okay. But you probably using their library, okay. Maybe it's based on TensorFlow. You will do the called the train function, okay. And then finally you can predict by giving images, okay. So this is when you have one object, right, one image patch with only one single object, it will have a neural network, convolution neural network, which for image feature extraction, to extract those final features, which is x1, x2 to xd. And based on that, you can define two loss functions. One is the cat, right? So what is in the box. Another is box locations, okay? xy is maybe the lower left corner, and the w and h are the width and height of the box, okay? And then you can minimize both the summation of them, right? Maybe with some weighted summation, okay? And so that the model will try to minimize both, right? Minimize the summation is minimizing both, so that you will get accurate boxes, and in the meanwhile, you also get the object in the box, okay?
So this explanation is based on if we decide to go the route of choosing our own project, because I don't think the data.
Yeah, you can choose your own project, but you should be as difficult as this project, okay? You cannot choose a simple project. That's what I mean? Comparable difficulty. That's why you need my approval. It's okay?
Correct. Yeah, I don't understand.
Without any help, he wrote that.
Yeah. I think. Yeah. Any questions?
Again.
Yeah,
I was just saying. Yeah, I was just saying. Yeah, okay. If we choose our own project, and it should be just based upon the explanation you just gave, But the data set that you're going to supply, which is off of the drone data set, the one that I guess we put up together in the previous assignment, it's not going to be just, I mean, it's not going to be, I know it's going to be data set full of image, but it doesn't apply to this explanation that you just gave.
Didn't apply to what? I didn't quite get it. So if you work on another project, you find some public data set, that's fine, okay? On Kaggle, etc. Okay. For this data set, I can only see you can do image detection or segmentation, okay? Object detection, okay. Yeah. Yeah, this data is just for this purpose, okay? If you find another data set, it's fine, but if you just run a SVM and report some, accuracy, you will get a very low score. Okay, you can go ahead with that. If you want to prove that, maybe the 4 mark is 80 for them. Okay.
Okay.
Yeah, because it's too simple, right? Right. So, yeah, if you can find an equal difficult and a more meaningful project, and it's not using from elsewhere, that's fine. Okay. Otherwise, you can stick to this project, right? So it's very clear, and you can try. Okay. And yeah, so that's what I want to say. So basically, as I said, so basically, in detection model, what we are doing is something like this. Okay, so so compared with localization, in detection, we will dig out those small patches that contains only one object, or potentially contain only one object, called region proposals. Okay, and when we have the region proposals, we throw them into a localization, something like this model. Okay, so this is all these models are doing. Okay. So here, all you care about is the final layer. Okay, so the final layer is the x1 to xd. Okay, and usually it has as a class, right? So this is a softmax. Okay, and the box is a regression. Okay, and you want to minimize them. Right. The only change you want to do is because maybe the pre-trained model has a class for 80 objects in Microsoft Cocoa. Right. Now we only care about 5 objects. I say the nut, the thread, etc. Okay, so you need to swap the last layer and retrain the weight matrices in the last layer. Okay, maybe there's a dense layer here. Okay, we'll teach that in the next class, so no worry about it. It's a fully connected layer with many weights. It's kind of like a logistic regression for each class. Okay, so that's kind of like this. Okay, and so this is what you need to do, right? So there may be more complicated way of doing things. Like there are different ways, but each just called a head. Okay, so this is like for class head, this is a box head. Okay, if you want a segmentation, right? So you want the pixels, you have the inside the box, you have another masks, right? So this is the pixel of this object, that is not, right? So it's a Boolean mask. Okay, and here's example, right? So fast RCN, mask RCN is a model that besides doing object detection where you have the class and the box, okay, well, this is the last fully connected layer that extracts the features, okay? You also have another model that takes the image, the feature image, you don't flatten into a vector, okay, as an input. And this will go all the way to a mask. Mask basically whether this is a yellow pixel, this is a yellow pixel, yes. 1, right? This is 0, okay? So they will learn this using another model called a fully convolution net, okay? So for that, again, you don't care about the details of these FCN details, right? You just care about what's input, what's output, and wire them together, right? And so here's a few models you can try, okay? So mask RCN, right? So the code is here. And if you look at the code, there are very detailed documentation on how you can do things. Right? And I know that there's also a post on machine learning mastery, which is a blog on how to use different tools. Right? There's a very detailed walkthrough on mask RCN, how to use that to detect your own objects, right? Using pre-trained models. Okay, and there's also one for YOLO, I think. So you can follow that and make an end-to-end model completely working on our data set. Okay, maybe not working well, but at least to make it work. Okay, so this is one step. Right, so this is basically the class head. This is the mask head. Okay. So there's a loss function also defined on the mask. The mask is basically a binary classification, right? So you know, so whether this is 0 or 1, right? It's a binary classification on each pixel in here. Okay, it's again classification. Okay, It's classification, regression, classification, but pixel-wise. I think somehow, yeah. So this is the paper, okay, if you want to take a look at that, but usually you don't really need it, right? Because this paper is describing those models, how it's designed. And an important thing about mask-ASEAN model or fast-ASEAN, this kind of model, is that RP network, or we call region proposal network. It just to say, hey, there should be an object here, right? And then you put to a localization model and do the prediction, okay? So there's two other loss functions relevant to location of the object. First, you do a binary classification, say whether it's a background or there's some object here, right? So this is binary. This also has a box and a class, right? The class is whether it's background or there's an object in it, right? And then if it's object in it, what's the coordinates? And these things will go here. So this is called a two-stage model, okay? First, catch those objects, okay? Catch somewhere there could be object, and then throw to another model where you adjust the location to be more accurate bounding the object, and also what's in the object, okay? So there are maybe box and the class and the box and the class, 4 heads already. If you have a mask, then there are 5 heads, okay? So this is mask ASEAN. YOLO may be simpler, right? So YOLO only has 2 heads. One is class, when it's class, when it's a bounding box, okay? So this is a potential implementation you can use. I'm not sure whether this is the best. You can try. And there's also a blog post on machine learning mastery that you can make it work, right? So, and so if you can do a good job here, you can also contact me for like research, right? So I think basically you have the capability to learn the model and make it work, right? So change the last few layers, okay? And so this is a paper associated with YOLO v3, and there's also v4 recently. Okay, you can also try that out. And v4 is by different authors from YOLO v1, v2, v3. Okay, so but you can see whether it works. And the YOLO is a little bit different, right? So it has a predefined grids. Okay, and based on grids, it defines so-called anchors around the grids. Okay, and based on these predefined anchors, it then throw to a localization model to detect what's in each anchor box. Okay, so there's nothing like first a proposed anchor box using another model to train. Okay, these anchor boxes are predefined. It's just that some of them are thrown away. Okay, because there's potentially no objects there. And there's also a retina net. Retina net is saying that it want to better differentiate from the background. Okay, so for example, you have well-classified examples, right? So so you want to adjust the loss, okay? Because if you have a lot of objects that are, the background have a lot of pixels, right? You want to give a low score, right? So for those objects that appear less often, you want to give a high score. So it has some change of the loss function, right? So remember, we talked about, cross entropy loss. It's really the log PT, right? T is a true class, okay? Now you have another weight adjusting that. If your class is not so probability is very low, it does not appear a lot, you can boost its weight a little bit, okay? This is called a focal loss. I don't know whether there's, but if you read this paper, there's something here, right? And there's an implementation here that you can also follow, okay? All these implementations are very detailed. For example, if you look in here, let me go to. So this should not be that difficult because all these research papers with normal models are like worked with undergraduate students in 2 months. Okay, so this should not be so difficult. Okay, so I don't know what's duplicate. Maybe there's a new torch vision module that you can directly use called in TensorFlow. Okay, so you can read this and how to install if you want to use this, and what's the loaded model, right? So this is a predefined model, maybe using ResNet. That's a pre-trained model. Okay, and then how to train. Right, using this script. Okay, so you basically are following their instructions. Okay, and then they will report some metrics. Okay, like the average procedure. And basically, it's an end-to-end walkthrough. Okay, and maybe you need to specify what are our classes. Maybe nut is 0, or you need to follow this, and then you show that you can detect those objects. Okay, in order to do that, you need to have a good understanding of classification, regression, right, and how they play in the box and mask, these kind of things, right? So this will help you understand, right? And the loss function are really the softmax and the mean square error that we have been touching upon, or maybe some variants of it. Like this is the focal loss, okay? It's a cross entropy loss with some weights, okay? And yeah, I don't know why there are so many. I think there should be no animation. Okay, so our drone data is shared. Okay, so if you click there, you can download it. Okay, so let me show you. So if you can see here, so this is all the photo images, and this is the annotation file into the images. Okay, so that's annotation file. So this is in JSON, so you should be able to parse the JSON. Okay, you need to import JSON, and then JSON just a Python object embedded with dictionaries and sets or list, right? So you need to extract those images and also their, their bounding boxes, okay? And then throw to the model. So this is the part of work that you have to do, okay? But there are more than 1 month, so that should be easy. And we also have some sample code actually, okay? I will show you later. And this is the third step, okay? You need to fine tune your model, customize and fine tune, okay? So here, whenever you have a pre-trained model, right? It's maybe on a source domain with car, motorcycle, etc., road, right? And now you have a target class, right? So bicycle, bird, sky, etc. It's different from the previous one, right? So what you would do is you want to reuse those models already trained, okay? They are pretty good at extracting image features, right? You just want to fine tune the last dense layers so that it maps from instead of car to bike, okay? Right, using the extract features. Okay, so you will retrain the dense layer at last. Maybe we'll propagate some weights earlier, okay? Fine tuning, right? How to do that? Each model has its instructions. Just read the website on how to fine tune your model with a new class, okay? So this is what you need to do, right? So last layer, how to wire loss functions, how to change this, okay? Keep in mind, nowadays in machine learning, in deep learning, no one use their own trained model from scratch. You always start from pre-trained models. Okay, there's a model zoo, right? And you can pick a model, and then you can use TensorFlow Hub to get the weights of the model that are pre-trained, maybe on 100 GPUs in Google. Okay, and if you want to train this yourself, it will take forever, right? If your gradient descent is already reached very good places, then you tune a little bit to your target domain. That's very close. Otherwise, this may take 1,000 years for you to do because they have 1,000 GPU servers. Okay. And so this again, then you need to report some metrics for our object detection problem. It's mainly average precision. Okay, so there are some concept average precision. Yeah, so for one class you can define average precision. This is really for binary classification, right? So if you have many classes, then you need to report the mean of their precision, average precision. Okay, and average precision again have a threshold, just like what we said, right? So if you have logistic regression, a sigmoid, right? And whether it's 50% or not. Okay, so there's the threshold here. In there, they also have a threshold. Okay, so this is the IOU, right? So if your true box and the estimate box is almost the same, right? Then you are correct. Otherwise, you are wrong, right? But how close are they? There's a threshold to control. Okay, so that's why you have like AP IOU 0.5, AP 0 IOU 0.75. Okay. And here's example, right? So what is IOU, right? So let's assume, this green box is the ideal box that the people annotated, okay? The red box is a detected box, okay? So what you will do is you compute their intersection, right? Divide by the union. That measures how good you are, right? So if you are overlapping it perfectly, it's 1, right? If you are totally not overlapping, it's 0, okay? So this is the concept of IOU called intersection of a union. This is intersection, this is union, right? You can look at the details here, right? But I believe there are functions like in TensorFlow that you can directly call to compute it, right? So, and those models may directly already have evaluation module for you to directly given the text data and get to the mean IP. Okay. So you don't even need to write your code to do that, but you need to understand what they reported, what's the meaning. Right? So this basically says that the IOU computed this value, right? Not too bad. Right? If you use 0.5 or 0.75, you are correct. Okay. And so this is the definition of average precision. Okay, you can take a look at, I think the first one is good. Okay, the second one maybe a little more details, but as long as you read the first one, you will understand the whole story. Okay, the last one is show best results, 10 best results. Okay, once your model is trained, you can of course detect the images on your training data, right? And you can also detect on the data that you have never used. Okay, right? We require you to, while you find the best, you can try to find 5 of the best from the training data, it's fine, okay? But you at least include 5 test images, show how well your model is doing on the test images, okay? Altogether 10 images, right? And here are examples for YOLO models, right? And for FastRCN, this is a advanced called a network architecture search, right? So basically for the convolution nets, those image feature extractors, they have some architecture search, okay? So this is something that's beyond the basic processing, okay? So this is the advanced model, I think integrated maybe in TensorFlow already, but it's not the one we request to use, okay? And there's also SSD, it's also the one stage model, just like YOLO, okay? You can also try them out. And so again, training on your own machine is fine, but if you don't have a GPU machine, one way is you can apply for Chiha account, right, from UAB, okay? Another is that you can use Google Colab. They provide a free GPUs. The problem is that you cannot train on all our data set, right? So because our data set is too big. If your Google Drive is free, then potentially you can only have 15 GB size. Maybe our image is too many. You can use a subset to train your data, okay? Maybe 10%, 1% is okay? Maybe or 20% of the images that you can fit in your Google Drive. If you have paid Google there, you have larger Google disk size, that's fine, okay? So basically Google Colab is a server. When you log on, it will give you a virtual machine with GPUs, okay? Sometimes it will give you a CPU machine, but you can configure it. Say, hey, I want a GPU, okay? And it's free GPU provided. Google is super rich, right? So I don't know why they want to do that, but now you don't have any reason to use your own machine in some way, okay? All the notebook files and all the data files you can read are from Google Drive. Okay, you can mount your Google Drive to that virtual machine, and then you can read data from Google Drive. And that's a way that even if you don't have a GPU, you can still use Google Colab. Okay, the cloud environment to do that. If you are not familiar with Google Colab, just look at here. Okay, Google Colab itself is a Jupyter notebook. It's a Google Colab notebook file. Okay, it's compatible to Jupyter notebook. Additionally, it gives you a virtual machine with GPUs, and the disk is using Google Drive. Okay, and you can read these materials to get familiarized. Okay, and actually we tried this model. Okay, it turns out that usually we have an image with maybe 80 objects, right? And the objects are very small compared with those images, right? So it's not going to be something like this, right? So if your image is this size, your object is this size, right? So it's still maybe 5% of the image. It's good, right? So in our case, our image, a lot of cases you have a lot of objects, but each object maybe is 0.5% of the image, right? So for those cases, these models don't work well, right? Because they will rescale the image, then those small objects become a pixel. Okay, one solution to tackle that. So a student tried; they can recognize a lot of the nuts, okay, but not all of them. Okay, then you will get some points deducted. Okay, for sure, right? So maybe to differentiate from those students doing good. Okay, but a solution is that you can do a sliding window, right? So you can slide here and slide here, right? So with some overlap, so that if you have an object that is falling here, right? So it will be captured by this model and also this model, right? If you have object that across the red box, you cannot see the whole object, then at least you have a blue box capture this object, okay? So that's the purpose why you will have an overlap ratio compared with your width and height, okay? So this code is actually already done here with an undergraduate student in the summer, okay? So you can reuse it, you can read the code, and it also gives you some hints on how to read the JSON file, okay? Of the VIA, okay? And so this is a code that you can use, right? So our criteria in this code is this, right? So if we get small patches, okay? And if there are some objects that's not complete, like this nut, right? It's not complete. We will not mark them. Okay, after you train, usually if your object is not totally contained in a box, we will the model will not mark it, right? Then you can take these small patches into the detection model, right? They will detect things like this. Okay, so this is a student who annotates things, not in an ideal case, right? So, but after training, you can see that this is using mask casting. You can really detect things that are better than the original annotation. Okay, but we have kicked out all those kind of bad annotations. So you can safely try, okay? And finally, you do want to merge them, right? So because you have so many boxes that are overlapping, maybe some objects are overlapping, detect twice or 3 times, okay? For example, here, this corner, you may detect the same object 2 or 3 times, right? So you want to keep only one of the box, right? So there's a algorithm called NMS, okay? Non-maximum suppression, right? TensorFlow has this function, okay? Then you can merge those images into one image, right? And you remove the 3 boxes into just 1 box. That probably is the using NMS algorithm, right? So that's the most likely box, right? The box is good, right? Because each box is associated with a class probability, right? So you probably choose a box with the most class probability among those boxes that overlap. Okay, you can do this, but this code is not provided. Okay, you have to write your own. Right? But again, you can call this function by putting the boxes here and give the score. Right, the scores can come from the class probabilities, right, from your softmax. Okay, there's some coding work here for sure. So we encourage like 4 students work together if you want to work on the whole thing. Right? If 1 student work on that, maybe the advanced topic we will not require you to do that. Okay, so but you will not get 100 marks, but we will deduct less points than if you have 4 students but still do the same thing. Okay, so that's basically the project. Okay, that's it for today. I think we already passed 1 or 2 minutes. Any questions?
Yeah, Professor.
Yeah.
The requirement, those are the functionality you would like to see in the implementation, right?
Yeah.
If those are the functionality, then why are we using transfer learning, or why are we mandated to use transfer learning in one of those requirements?
Transfer learning, right? So you can if you don't use transfer learning, you can try yourself. Okay. So the reason we want to use transfer learning is because you can directly download their model parameter. Okay, load them. Okay, the theta you can load them because this theta Google maybe spent 1 million to train it. Okay, then you can reuse it. Okay, and then train your model. Okay, Google use all those their images and train already pretty close to your optimal. Okay, because now the weights are changed, but the features are good. Okay, then you can fine tune the weights so that it matches this. Okay, this is faster. If you retrain, our images, number of images is not sufficient. You need 100 times more images. Okay, but you can try. If you can try equally good without transfer learning, no worry. Okay, you can try that. But
I think you sort of over answered my question. Basically, what I'm trying to get to is,
yeah,
you want to see a process where the model is being fine tuned, right?
Yeah,
so instead of using transfer learning, I'll think, changing or the regularizing parameters in order to fine tune the model is part of fine tuning the model. Is that not correct?
Yes, the fine tuning is basically for each of the model, they will tell you how to load a pre-trained weight, okay, in the instruction of the GitHub. And you just load them, and then you replace the last dense layer, for example, or the boxed layers. Okay, boxed layer maybe you don't need to change. Okay, and then you fine tune your model. Okay. So basically, all these GitHub libraries are just for you to fine tune. None of them will allow you to train from scratch because you need to train that with Google's data and with a lot of resources. It's okay?
Yeah, kind of.
Yeah. Because we are over time. So if the other students don't want to stay, you can leave. Okay. So I can give you an example. So just to clarify things. Okay. Let me see. Select a model. Let's just look at, let's say this library. Okay. I think they have some examples. Let me see. Maybe you can go to their, let me see why I cannot find my mouse. Go to samples, right? And there will be some examples to go through, okay? If you look at their model, okay, how they do it. Basically, they will first load a pre-trained weight, okay? And then replace the last loss function, okay? So let me see. I think it should be HD5. Let me see. So you will first load the image and data set. I think potentially it's called a load model, this one, load. But anyway, yeah, so it's too detailed, but basically you go through this, it will tell you how to do that. Okay, so basically they have the model library and it will already have a default weight for you, right? So when you do gradient descent, you already should be somewhere, okay? Right? You want to make sure you are very close to the optimal, okay? You don't want to be here. So it will ask you to load this pre-trained weights and then you do gradient descent. It's okay? All you need to do is load their weights, okay? And then change the loss function at the last layer, then do gradient descent. It's okay? Do I answer your question?
It is. Yeah, it is. I think I'm trying to. Basically, what I'm trying to find out is, so are we encouraged to actually use transfer learning for any of the project, either the one that we picked up or the one that you are giving us?
Oh, you don't have to use transfer learning. For example, for simple problems like image segmentation, you can train from scratch. Okay, so like a brain tumors, etc.
If you don't use, that's my question. If you don't use transfer learning, and in fact, one of those criteria and the requirement will not be met, so that means we're going to lose points for not using transfer learning in that regard. Isn't that correct?
This is your question, right? So if you are, let's say you are trying a segmentation model, right? So that's fine. So you just customize and fine-tune a model. We never mentioned that you need to use transfer learning. Okay, fine-tune or train. Okay, yeah. So but for this particular application, you do need a.
That's what I was saying. When you fine tune it, I mean, we can change the parameters, regularization parameter to fine tune the model. Would that be sufficient enough to get?
Yeah, that's sufficient. Okay, if you transfer from scratch for another application, this application will not work out. That's sufficient. We never say you have to use a pre-trained model. Okay, so fine tune you can replace with train. Okay. Right, so you can train and then fine tune. Okay, so for this particular case, we do require you to do transfer learning, and the transfer learning is actually mentioned. Let me see, where's the transfer learning? What do you see the transfer learning term?
I mean, when you went to that, that was on item 3, that's all you talked about in item 3, I think.
Oh yeah, so this transfer learning is just an image title. Okay, so you can do this. Okay. Right, so this is not a requirement. Requirement is just you need to customize the model and make the model work. You need to train your model. It's okay?
Okay, yes.
Yeah.
Thank you.
You're welcome. Okay, I see Anara is still here. Let's do this. Okay. Any questions? If you have no questions, we will. Yeah. So it's just a little bit more than 1 month, right? So 1.5 months. Okay. Try to.
Professor.
Okay.
Professor.
Yeah.
Yeah. I mean, which model do you think is best suited for our case? Like, which model should we transfer learn? Like ResNet, Inception V3. I mean, which model?
You can use any model. Okay, so you can use any model. For example, if you look at the YOLO V3, right? YOLO V3. Okay, like example, right? So maybe there are machine learning mastery already tell you how to do that. So we allow you to do this as long as you can make things work. You go through these tutorials, make things work. It's fine. Okay, they will tell you step by step with documentation. That we have no requirement other than making things work. Okay, you can refer to those things and tell you line by line how to do things. It's okay?
Yeah. Okay.
You just choose a arbitrary model and make it work. Okay, on our data set. And we do remind you that it may not work perfectly without cropping. Okay, if you don't want to merge but you want to crop, right? That's fine. Okay, you can use our cropping data shared here and crop it as a train. Maybe you direct train, it will not work. Okay. you can crop it, like crop it, and then using the crop data to train. That's fine, okay? And then you should be able to detect things, right? In general, we hope so actually, I'm pretty sure the first time you try, it will not work out unless you crop, because the object is too small compared to the image, okay? And you can directly crop in the train, that's acceptable, okay? But it will not be 100 point, okay? If you want a 100 point, you want to write the MS code to merge them back, okay? And these will include how you reposition those boxes, right? Because after crop, the boxes is now 0, 0. Now, if you go put it back, it's not 0, 0, okay? It's somewhere in between. And boxes also need to shift it, right? So that's
Can we use Keras for?
Yeah, you can use any library. Okay, there's no restriction in any kind. Okay, as long as you can make it work. So again, we just want you to be able to work on a big project end to end. That's all the requirement. Okay, but you do need to have these things like you use the data, right, and you select a state-of-the-art model. Don't use a SVM. Okay, and then you fine tune, you train your model, you report the results, and you visualize your results. That's all we require. It's okay.
Yeah. Okay.
And if you think this is not working out, you can discuss with me. We discuss some other projects. If it's simpler, we will adjust the score accordingly. Okay. Again, so if it's very simple, like working on some tabular data, then you use SVM and report the metrics, that's too simple. Okay. Again, I would encourage you guys to start early, okay, because it will take time. Okay, this is the final project. Beyond that, we only have one written assignment and one the Newton method project. That's all we have left. Okay. Yeah, that's it. Any other questions? If not, so I will disconnect and I will send this slide tonight to to Canvas. Okay, so that you can get there and you can download the data and start to play with it. Okay. Thank you. And feel free to send me email if you have any questions. Let me find my mouse.